I hope you are all having a good morning. I am Mr. Ish. Thank you for joining me. Here we are looking at position and time graphs. Very recently we understood and we interpreted velocity and time graphs. This is something similar to that, highly relevant 12th grade level physics and math material. Think about position as where an object was to where it ended, and it's given the symbol S. When you're talking about position and time graphs, when you do the change in position divided by change in time, you get your velocity. So when you're looking at these graphs, the slope will give you your velocity. Just like how you do distance divided by time to get the speed or the rate, velocity is equal to change in position divided by change in time. You can think of it as this: final position minus initial position divided by final time minus initial time. And that right there can be very similar to a slope formula, y2 minus y1 divided by x2 minus x1. You can think of everything like this for linear lines, straight lines. When you have curves, then obviously you have to start thinking about calculus. But in this material, we're going to keep things very relevant to your level of high school math and physics. Remember, position is where an object was to where it ended up. Given that, let's look at this graph right here. We're going to be utilizing the same numbers. Time is always with regards to seconds on the x-axis, position with meters with regards to your y-axis, and we'll have 20. We have a line which looks like this. I would recommend you develop points 0, 0. At time 0 we're at 0 meters, and at 5 seconds we're at 20 meters. Always think about this as your rest position when you're talking about this term position, and this ends up as your final position. All right, and what you end up doing is regards to movement of an object. If you calculate the slope over here, you're looking at 20 meters divided by 5 seconds, you get 4 meters per second. And now you're seeing that the slope is giving you a velocity value. Because it's a straight line, you can come up with a bunch of interpretations from this graph. Velocity is always constant. Velocity here is also always positive. Velocity is not changing. Since velocity is not changing because you have a straight line, you have zero acceleration. Remember, if the velocity does not change, as you know from acceleration being change in velocity divided by time, if the velocity does not change, you have zero acceleration. And lastly, here's one, here's another one, and the other one is your object moves. And how much does it move? You know here, it moved 20 meters. So when you have a straight line graph aimed upwards, position versus time, these are the conclusions you make. Velocity is constant and it's positive. Your acceleration is 0 and your object moves. So at all instant of time, you're always moving only at 4 meters per second. And you can say very roughly you have a speed here of 4 meters per second. Let's look at a graph which looks like this. A flat line, you know, in terms of slope, these are always equal to 0. But let's come up with our points. At time 0 we have 20 meters, and at time 5 we have 20 meters. What does that mean? Your object is at some position but it never changed in that terms, and the object never moved, it never changed its position. Since the slope over here is 20 minus 20 divided by 5, which is equal to 0, it tells you your speed or your velocity, velocity being the better term, is 0 meters per second. The conclusions you make from this graph is object did not move. Object has 0 movement. Let's keep it easy like that. Object has 0 velocity. There's no velocity. There's 0 acceleration. There's no movement at all, and there's no displacement here at all. The best thing you can say over here is your object is at rest. And these are the conclusions you'd make. I'm not saying rest here as your resting position. I'm just saying wherever it is, your object is just staying over there. So with regards to its position, it's at rest. Now you have a curve which looks something like this. Start with your points. You have 0, 20. At time 0 you're at a position of 20, but at time 5 you're at a position of 0. If you were to do the slope, you know you're getting a velocity here. You're getting a 0 minus 20 divided by 5. You're getting minus 4 meters per second. Here the minus would indicate that you do have a velocity, but you don't have a negative velocity. It would tell you the direction of where you are going. That's how you would interpret the negative sign. But what are the conclusions you make over here? Because it's still a straight line, your velocity is still constant. It's not a changing velocity, but it's a negative value, means you're returning back to an original position because you're going in the opposite direction. Because velocity is constant, you have 0 acceleration. To have acceleration, you must have a change in velocity, but you don't have a change in velocity because you have a straight line over here, 0 acceleration. Remember, when you're looking at the velocity and time graphs separately, the straight line indicates acceleration because in that instance, you're looking at velocity being changed. But here in the position and time graph, you have a constant velocity. Velocity is not being changed, so you have zero acceleration. And another conclusion you can make, since you're going from 20 up to 0 in terms of your meters, your displacement, your object is, you can say now, returning. Object is returning to rest position or resting position. So that's how you can interpret these type of graphs. This particular graph right over here. The next two graphs we look at will be graphs which have non-linear lines, but we won't get too technical with regards to derivatives. We'll keep that entirely out of the picture. We just talk about interpretations only. We have a graph which looks like this, a curved line. You know, at time 0 you're at 0 meters, but at time 5 you're at 20 meters. Nothing over here is uniform with regards to constant change of your position. Initially you might have obtained very little in terms of position. Like at time whatever, let's say 4 seconds, you're only up to here in terms of position, but in the last 1 second you did a huge increase in position. That's how you would interpret this. In this particular instance, if you do the slope of this by means of derivatives, we're not doing it, but you would come up with these conclusions. Velocity is not constant. It's a ever-changing velocity value over here. At a particular time you might have a low velocity, but at a different time you might have a much higher velocity. If velocity is not constant here, you'll have acceleration. You'll see acceleration because there's a change in velocity, so you'll see that. You'll see a change in velocity. It's non-uniform, it's not constant, but the velocity here in all instances is positive. Because the acceleration is present and velocity is a non-constant, non-uniform positive value, you can say here the object is accelerating, and you can come up with this very good conclusion right here that your object is indeed accelerating, and lastly your object is moving. So these are the four conclusions I would make from this type of a graph. Our last graph looks something like this. Is the curved line, but you see how it's going. It's in a downward trend. At time 0 you're at 20 meters, but at time 5 seconds you're at 0, which means your object did eventually return to a resting initial position, so there is movement. We don't have to do slope determination here because you have to do derivatives, and I don't want to make this too technical, but the conclusions you would make over here is of course your object is moving, but it's moving to a return position. You have a velocity here, you'll have a change in velocity, because if you did the slope determination, it's not a linear line, it's a curved line. You'll have a change in velocity. Your velocity will be not constant, because there'll always be a changing velocity based on what time interval you're looking at, and your velocity will be negative. Because you have a change in velocity, you will have acceleration present over here. The only thing is the acceleration will be a changing acceleration, and you'll see that since your velocity is decreasing with time, you're seeing a deceleration. You can call that a deceleration. Your object is decelerating in the manner such that the object will return to a rest position, and eventually the velocity will zero out because the movement will stop. So what you have over here, as you can see, is you have non-uniform motion, because everything here is not linear with regards to that line. Non-uniform motion. You have non-uniform velocity, you'll have non-uniform acceleration, and you'll have an object which is non-uniform in terms of its motion. You may have a great decrease in position very early on, and towards the end, in the last 1 or 2 seconds, you'll have a very small position that will be covered in that time interval. But that right there is how you interpret position and time graphs. The linear lines are much easier to interpret than these curved lines, because they require you to do derivatives and then evaluate based on which time interval you are at for your conclusion. Because if you do tangent lines or slope determinations at each of these particular points, you'll have a different slope value, and that different slope value will lead you to a different conclusion. But that's everything here, position and time graphs in a nutshell for you all. Thank you for watching. Have a good day.